Hello. To understand the elements of the integers modulo n that have multiplicative inverse, we need to recall some of the basic properties of the greatest common divisor of integers. Along the way, we recall what is Euclid's algorithm and what is Euclid's lemma. Okay, let's recall what is greatest common divisor of two integers. We are not going to assume that both of them are zeros, so at least one of these integers are going to be non-zero. That's part of the assumption. So suppose I give you a and b, and at least one of them is non-zero. Then the greatest common divisor, as the name suggests, is the maximum among all the common divisors of a and b. So if I look at the set of all the common divisors, d integer, d divides a, and d divides b, I take the maximum of that, and that would be the greatest common divisor, or simply GCD of a and b. First thing that we have to notice and remark is that there is such a maximum. And the reason is that every common divisor, any divisor of a, if a is a non-zero element, is going to be at most absolute value of a. Because a is supposed to be d times some integer, I take the absolute value of both sides, and I get that absolute value of d, so let's write it down. So if d divides a, then a is d times k for some integer k. Now I compare, I take the absolute value. Now assuming that a is not zero, then I deduce, so if a is not zero, so let's take this a bit higher. If a is not zero, then neither d nor k can be zero. And when k is not zero, its absolute value is at least 1. And from here, we can deduce that absolute value of d is at most absolute value of a. And of course, d is at most equal to its absolute value. So altogether, we get that every divisor of a non-negative integer a is at most equal to its absolute value. So in particular, every element, every common divisor of a and b is going to be at most equal to the minimum of the absolute values of a and absolute value of b. And here you see the importance of the assumption that at least one of a or b is supposed to be non-zero. If both of them are zero, then of course the GCD would be kind of infinity, because every divisor would be a common divisor of zero. Every integer is a divisor of zero. Now, assuming that at least one of these integers, a or b, is non-zero, we deduce that the set of common divisors of a and b have an upper bound of the minimum of the absolute value of a and absolute value of b, and therefore it has a maximum. And the maximum is called GCD. So GCD of AB is an integer which is at most minimum of the absolute value of A and absolute value of B. Pictorially, it's like this. I am giving you a rectangle, an A by B rectangle, and I want to cover this rectangle by squares. What is the largest size square that can cover this A by B rectangle? That size is the greatest common divisor of A and B. So that's the pictorial way of thinking about the greatest common divisor of two integers, at least two positive integers. So for instance, when I give you 12 and 21, I look at the rectangle, that's 12 by 21, And this rectangle can be covered by 3 by 3 squares. I need 4 by 7 3 by 3 squares in order to cover a 12 by 21 rectangle. That's our GCD. To find what this tile is, we can apply this type of a greedy process. We start by saying, okay, so every square, if I can cover the entire thing by certain squares, then I can cover the 12 by 12 subsquares that I get out of it. So what we do, we start with this 12 by 21. We say, okay, so if I can cover it with whatever small squares, then this 12 by 12 square on the left side of this rectangle will be covered by the same thing. So the remaining part should be covered by the same tile. So essentially, I can cut this larger square, this large rectangle. I can cut this 12 by 12 square and ask the same question for the smaller rectangle and ask, okay, what is the largest square that can tile this smaller one? Whatever square can tile the smaller one is good enough to tile the larger square and therefore the large rectangle as well. I can repeat this process. I can cut squares one after another till the remaining shape is a square itself, and that would be our result. That would be the largest square that we were looking for. So again, in the case of 12 by 21, we can say the following shape as a way of finding the GCD of 12 and 21. So we start cutting. We cut first. We get this 12 by 12 rectangle. 12 by 12 square. We cut it out. We get a 9 by 12. We get a 9 by 12 rectangle. And then we repeat the same process for this 9 by 12 rectangle, meaning I cut out this 9 by 9 square, and the remaining rectangle would be 3 by 9. I repeat this, and I end up cutting this 3 by 3 square out of this 3 by 9, and the remaining rectangle would be 6 by 3. And I do the same for this rectangle, and cutting out this 3 by 3, the remaining shape is a square. It's a 3 by 3 square, and that's our GCD. This process is essentially Euclid's algorithm. Now, what we will do next is make this process more formal and prove why it actually works. To do so, I'm going to recall some of the basic properties of divisibility. So suppose a, b, and d are 3 integers, and d divides a and b. From there, we can deduce that d divides every integer linear combination of a and b. When I say integer linear combination, I mean integers of the form r times a plus s times b, where r and s are integer numbers. So again, the claim is that if d divides a and b, if d is a common divisor of a and b, then d divides ra plus sb, no matter what integers r and s we pick. The second part of the claim is the following, that if d divides b and d divides a minus b, then d divides a. As we will see immediately, it is a particular case of the first claim, but it is of importance for us, so that's why I've isolated this special case and mention it separately. Okay, so again, if d is a common divisor of a and b, then d divides every integer linear combination of a and b. If d divides b and d divides a minus b, then d divides a. So these are the claims that we want to show. Let's start with the more important one, which is the first one. The assumption is that D is a common divisor of A and B. That means both A and B are integer multiples of D, which means A is k times D for some integer k, and B is L times D for some integer L. Now I'm interested in this linear combination, integer linear combination of A and B, RA plus SB. Let's plug in a KD for A and LD for B in RA plus SB and see what we get. RA plus SB is equal to R times, instead of A, I'm going to write down KD, plus S times, instead of B, I'm going to write down L times D. Now D is common in both of these terms. I can factor it out, and I get that it is RK plus SD times D. Notice an integer, the set of integers is closed under addition and multiplication. Therefore, knowing that R, K, S, and L are integer numbers, we can deduce that this term is also an integer. Altogether, we are deducing, we are obtaining that this integer is an integer multiple of D, is a multiple of D. So D divides RA plus SB. That's exactly what we wanted to show. Now, to understand the second part, it's enough to notice that A is nothing but 1 times B plus 1 times A minus B. So A itself is an integer linear combination of B and A minus B. So using part 1, we deduce that knowing D is a common divisor of B and A minus B, we can deduce that D is a divisor of A. Now let's see how this is relevant to what we discussed earlier. But before that, I'm going to mention the following corollary. So it is related to this process. So notice that in this process, what we are doing, if we are assuming A is more than B, or at least B, and then we say GCD of A and B is the same as I subtract B. GCD of B and A minus B. That's what we are claiming. So we are saying that in this process, we are changing the size of these rectangles, making them smaller and smaller, but along the way, we are not changing the greatest common divisor of the sides. That's why when we end up getting a square, that should be our result, because when I give you a square, greatest common divisor of a number by itself is, of course, that number. So we are introducing, we are giving a process through which the size of these rectangles are getting smaller and smaller, but the GCD doesn't change till we end up getting a square, and that would be the answer. That is what we are doing. So next, what we are going to show is, in fact, that every step is valid and doesn't change GCD, meaning GCD of A and B is the same as GCD of A minus B and B. That's what we are going to prove next. So if A and B are two positive integers, being positive is actually not crucial, but let's say they are positive. So suppose A and B are two positive integers, then GCD of A comma B is the same as GCD of B and A minus B. What is crucial is that at least one of them is non-zero, and at least one of them is non-zero, and the same for A and B and B and A minus B. So this is the important assumption. Otherwise, GCD doesn't make sense. For simplicity, I'm going to assume that both of them are positive. Okay, I want to show that greatest common divisor of A and B is the same as the greatest common divisor of B and A minus B. Remember, GCD is the maximum among the common divisors of these two numbers. So if we show that every common divisor of A and B is the same as a common divisor of b and a minus b, we are done. So if we show that the set of common divisors of the first pair of integers and the set of common divisors of the second pair of integers are the same sets, of course their maximum would be the same. So that's going to be our aim. We start with a common divisor of a and b. We show that it is a common divisor of b and a minus b and vice versa. Therefore, these pairs have the same set of common divisors. So suppose D is a common divisor of A and B. As we proved in the previous lemma, D is going to be a divisor of every integer linear combination of A and B. In particular, it's going to be a divisor of 1 times A plus -1 times B, which is A minus B. So D is a divisor of A minus B. D is a divisor of B. So D is a common divisor of these two numbers, B and A minus B, as we claimed. Now let's go the other way around. Now suppose D is a common divisor of B and A minus B. I want to show that it is a common divisor of A and B. It is already a divisor of B, so it's enough to show that it is a divisor of A. But this we have proved in the previous lemma. We show that if D divides B and D divides A minus B, we can add them up. We see that D divides A. So D is a common divisor of A and B. Again, GCD of AB is the maximum common divisors among the common divisors of A and B. This set, if D is a common divisor of A and B, it is a common divisor of B and A minus B, and vice versa. So these two sets are the same. In particular, they have the same maximum. Max of this set is GCD of B and A minus B. That finishes proof of this corollary. Now let's see how this corollary justifies the pictorial argument. So when we are given this rectangle, A by B rectangle, when we cut this B by B square, we end up getting a rectangle that is A minus B by B. This corollary says GCD of AB, GCD of the first sides of this first rectangle, is the same as GCD of sides of the next rectangle. So even though we are getting a smaller rectangle, we are not changing GCD of the sides. So following this process, at some point, we end up getting a square. In that case, the GCD of the sides is precisely the size of one side, and that's it. So this shows that along this process, we are not changing GCD, we are not changing GCD, and at the end, we get a square with sides equal to the GCD of the first rectangle, GCD of the sides of the first rectangle that we started with. That's why this pictorial argument actually works. And as I've indicated earlier, this is tightly related to Euclid's algorithm. So let's recall what's Euclid's algorithm. But before actually saying what Euclid's algorithm is, let me point out an important lemma. This important lemma is going to help us to prove why Euclid's algorithm actually works. And it is a nice lemma. It has applications as well by its own. So what is the state? Suppose A and A prime are congruent modulo n, and n is some non-zero integer. Then A, the GCD of A and n, is the same as GCD of n and A prime. So if A and A prime mod n are the same, their GCD through n with n should be the same. So if A and A prime are congruent mod n, then A and n have the same GCD and A prime and n. So this n and A and n and A prime have the same greatest common divisors. So that's the claim. And we'll see the connection between this and Euclid's algorithm. Okay, let's start with hypothesis. We are told that A is congruent to A prime modulo n. What does that mean? This means their difference is an integer multiple of n. So A minus A prime is nk for some integer k. Now, I want to say that GCD of A and n is the same as GCD of A prime n. Similar to the previous lemma, we are going to show that every common divisor of A and n is the same, is a common divisor of A prime and n, and vice versa. So the set of common divisors of A and n is the same as the set of common divisors of A prime and n. So that is what we want to show. Let's start with a common divisor of n and A prime, and I am going to show that it is a common divisor of n and A. So suppose d divides n, d divides A prime, then we know d divides every integer linear combination of n and A prime. In particular, it divides k times n plus 1 times A prime. This is, from this equation, you see that A is nk plus A prime. So this is precisely A. So we are deducing that if D is a common divisor of n and A prime, then it divides A, which means it is a common divisor of A and n. So we showed that a common divisor of n and A prime is a common divisor of n and A. Now I'm going to show the other way around. Suppose D is a common divisor of n and A. Now, from here, I know A prime is A minus nk. So it is an integer linear combination of A and n. By the same lemma that we showed, we know when D is a common divisor of n and A, it is a divisor of every integer linear combination of A and n. In particular, it divides 1 times A plus negative k times n. And again, looking at this equation, this side is nothing but A prime, and therefore D divides A prime. D divides A prime, D divides n. So knowing that D is a common divisor of n and A implies that D is a common divisor of n and A prime. Again, altogether we get that the set of common divisors of n and A is the same as the set of common divisors of n and A prime. Therefore, their maximum are the same. The maximum of the left-hand side is the GCD of n and A, and the maximum of the right-hand side is GCD of n and A prime. That's exactly what we wanted to show. So if A is congruent to A prime modulo n, then GCD of A and n is equal to GCD of A prime and n. Now, let's recall what is Euclid's algorithm. Euclid's algorithm is a fast way of finding GCD of two positive integers. You know, if you don't know, let me just tell you that at the moment we don't have a fast way of finding prime factorization of an integer. So one way of thinking about GCD is finding the prime factorization of the first one, then finding the prime factorization of the next one, and looking at the largest power that the smallest power that they have. So among these prime factors, we look at the minimum of the powers. So that's one way of finding GCD of two numbers. But algorithmically, it's extremely hard. At the moment, we don't have a polynomial complexity for factoring an integer into its prime factors. So this method is not quite fast from algorithmic point of view, but Euclid's algorithm, in contrary, is extremely fast and it's extremely simple. So what is it? I give you two positive integers, let's say a and b, and you want to find the greatest common divisor of a and b. What Euclid does is the following. He introduces this sequence of non-negative integers. So the first one is the max of a and b. Let's denote it by a sub 0. The next one is the minimum of a and b. So suppose a is at least b, so we set a sub 0 to be a and a sub 1 to be b. And we divide a sub 0 by a sub 1. We get a quotient and a remainder. Let's call the remainder a sub 2. So we get this equality. A sub 0 is a sub 1 times the quotient plus the remainder. In particular, we have that a sub 0 is congruent to a sub 2 modulo a sub 1. So a sub 0 is congruent to a sub 2 mod a sub 1. Now, the lemma that we proved shows that if a sub 0 is congruent to some other number mod a sub 1, then GCD of this pair is the same as GCD of this pair. So GCD of a sub 0 and a sub 1 is the same as GCD of a sub 1 and a sub 2. This means that through this process, even though the indices are getting larger, GCD of two consecutive numbers in this sequence stays the same. So next I'm going to divide a sub 1 by a sub 2, as long as a sub 2 is not 0. If it's 0, then I stop. So if a sub 2 is not 0, I continue dividing a sub 1 by a sub 2, take the remainder, call the remainder a sub 3, and do it again and again. And as we have discussed, along this process, even though I'm making my numbers smaller and smaller, I'm not changing the GCD. So at some point, the remainder will be 0, in which case we are done, because GCD of a 0 number with some non-zero number is that non-zero number. Okay, let's go through these steps a bit slower. So again, we divide a sub 1 by a sub 2, assuming that a sub 2 is not 0. And we repeat this till we get to 0 as the remainder. Altogether, what did we get? We have the sequence of numbers. A sub 0 is a sub 1 times the quotient plus the remainder. Then we divided a sub 1 by a sub 2. We get a sub 1 is this a sub 2 times this quotient plus the new remainder. And we continue till we get to the 0 remainder. Okay, now what do we know? We have discussed that GCD doesn't change. GCD of a sub 0, a sub 1. You see, a sub 0 is the same as a sub 2 mod a sub 1. By the lemma, we deduce that GCD of a sub 0 and a sub 1 is the same as GCD of a sub 1 and a sub 2. By the same argument, GCD of a sub 1, a sub 2 is the same as a GCD of a sub 2, a sub 3, and so on. At the end here, we have the GCD of a sub n minus 1. You see, a sub n minus 1 is a multiple of a sub n. Therefore, the GCD of a sub n minus 1 and a sub n is a sub n. Remember, a sub n is positive. This is the first time that we reached to 0. And a sub n minus 1 is a multiple of a sub n. So their greatest common divisor is a sub n. And through this process, each time I'm reducing the size of my integer. A sub 1 is strictly more than a sub 2 because a sub 2 is the remainder of this division. A sub 2 is strictly more than a sub 3, and a sub n was positive till we reach to 0. So through this process, you see that GCD of this guy is the same as GCD of the next one. These guys are the same. GCD stays the same. This means that a sub n is GCD of the first pair, And the first pair is just A and B. So A sub n, the last number that we get, the last positive number that we get through this process is precisely GCD of A and B. So in this process, we end up getting this strictly decreasing sequence of integers, and the last non-zero entry is the GCD of A and B. Okay, so that's Euclid's algorithm. But this algorithm gives us much more information about the GCD. Looking at this process, we see the following, that we have this formula. Looking at the ith row, we have this fact that A sub I minus 1 is A sub I times Q sub I plus A sub I plus 1. That means what? That means A sub I plus 1, the next one, can be computed in terms of A sub I and A sub I minus 1. We can capture this in the following matrix multiplication. This is an amazing matrix multiplication. When you learn about continued fractions, you see a similar kind of matrix multiplication. Okay, so let's see what it is. Let's look at the matrix that has the first row 0, 1, and the next row is 1, negative Q sub I. And let's multiply this by the column vector A sub I minus 1, A sub I. As I multiply this, what do I get? I end up getting a column vector. The first entry is, I have to multiply 0 by this and 1 by this. So 0 by A sub I minus 1 plus 1 times A sub I. I only get A sub I. The first row is a magic of bringing this guy up. So this is just A sub I. Now let's look at the bottom, the second component. I get 1 times A sub I minus 1 plus negative Q sub I times A sub I. Now we see over here, A sub I minus 1 minus A sub I Q sub I is nothing but A sub I plus 1. So I get A sub I minus 1 minus A sub I times Q sub I, and that is precisely A sub I plus 1. So all of a sudden, when I multiply by this matrix, I'm just shifting this column vector by 1. I'm shifting the indices by 1. Okay, so I can apply this for I equals to 0, for I equals to 1, and so on. Each time multiply by this matrix and shift the index till we reach to the last index that we worked with, meaning this one. This is after applying n matrices. So again, when I multiply by this matrix, I start with the first pair, A sub 0, A sub 1. I multiply by this matrix. Using this computation that we have over here, we know that when I multiply by this matrix, I have to only shift the indices, and I end up getting A sub 1, A sub 2. So instead of having this, I can write down, instead of the first one, I can write down A sub 1, A sub 2. As I multiply by the next matrix, I end up getting A sub 2, A sub 3. I keep multiplying by these matrices, and I keep shifting the index by 1, by 1, by 1, till I shift it n times. When I shift it n times, I get A sub n and A sub n plus 1. But A sub n plus 1 is 0, as we have seen over here. So altogether, we get this equality. You see, we get that as I multiply these square matrices one after another to the initial pair, column vector pair, I end up getting A sub n and 0. In particular, you see, all of these matrices are integer matrices. So as I multiply all of these square matrices, I end up getting another integer matrix. Now, as I multiply this integer matrix by this column vector, the first entry is supposed to be a sub n. That means a sub n can be written as an integer linear combination of a sub 0 and a sub 1. Now, what is a sub n? A sub n is the GCD of a and b. What is a sub 0? Is a. What is a sub 1? Is b. So altogether, we are getting this beautiful theorem that says that if a and b are two non-zero integers, then GCD of a and b is an integer linear combination of a and b. We have almost proved this, not completely. We proved it when a and b are positive integers, because Euclid's algorithm, the way that we presented it, worked only for positive integers. Here I have to take care of it, make sure that it is actually true for every integer, but that is rather easy because greatest common divisor of a and b is the same as the greatest common divisor of absolute value of a and absolute value of b. And if a and b are non-zero integers, their absolute value is definitely positive, and therefore I am working with greatest common divisor of two positive integers. Now, if I replace this with absolute value and absolute value, it doesn't matter because they change only up to sign. Absolute value of a is plus minus a. Absolute value of b is either b or negative b. So knowing this result for positive integers is enough to deduce it for every integer, and that's it. We get the desired result out of this Euclid's algorithm. Okay, so another way of interpreting this theorem is saying that this equation GCD of AB equals to AX plus BY has an integer solution. Now, if we look at this equation over here, this matrix multiplication, we see that in fact this Euclid's algorithm gives us q sub i's, and therefore using this matrix multiplication, we get an algorithm for finding an integer solution for this equation. So Euclid's algorithm indeed gives us an algorithm for finding, for solving this Diophantine equation. We call it the Diophantine equation because we are looking for integer solutions of this equation. Okay, so let's see an application, an example of this Euclid's algorithm, how it can help us to find GCD of two integers, and how we can find out a solution for the equation GCD equals to AX plus BY, an integer solution for such equation. So here is a concrete example. We want to find the GCD of 197 and 79, and we want to write it as an integer linear combination of 197 and 79. Euclid's algorithm says that I need to do repeated divisions. So we start calling the larger one a sub 0 and the smaller one a sub 1. I divide a sub 0 by a sub 1. I get a quotient of 2 and a remainder of 39. Of course, I have done this computation before. Now the quotient we call q sub 1, that's 2, and the remainder we call a sub 2, that's 39, and we'll repeat this process. We divide a sub 1, which is 79, by a sub 2, which is 39. Again, we end up getting a quotient of 2, and this time the remainder is 1. So the quotient is called q sub 2, and remainder is a sub 3. So this time, a sub 2, which is 39, is in fact a multiple of a sub 3, and therefore the remainder is just 0. The quotient this time is 39, and remainder is 0. And we stop. Euclid's algorithm tells us that this last non-zero entry in this process is the GCD. Therefore, GCD of 197 and 79 is 1. Okay, so in this particular case, it was actually easy to find out that GCD of these two numbers is 1. But it is not easy to write 1 as an integer linear combination of 197 and 79 without using this process. It is possible, I'm not ruling it out, but it is not as straightforward. Now, the algorithm that we have says that the last pair, 1, 0, if I put it in the column form, is equal to product of these matrices 0, 1, 1, negative q sub i's. I multiply them one after another, and then multiply this by the initial pair that we have. So by Euclid's algorithm, we proved this equality. Now it's enough to understand what is this matrix multiplication. So we plug in this q sub i's that we have and compute this matrix multiplication. So the first one is this one, it's the largest one, so let's put it on hold and let's compute this product first. So as we compute this product, we end up getting it is 1, negative 2, negative 2, and 5. You see, often this 0, 1, it's easy to compute. This just puts this guy, I mean, when I multiply this 0 doesn't do anything. So this 1 brings the second row to the first row. So that's why this is just the second row. And I do this computation for the second row, and I end up getting that it is negative 2 and 5. Instead of computing this product, always when we are interested in this kind of Diophantine equation and we are using this Euclid's algorithm, we don't care about the second component, in the second row of the whole multiplication. We only care about the first one because this is our GCD. This is the number that we are interested in, and that is only the first component of this column vector. And in order to find the first component of the column vector, we need only the first row of this matrix. We don't care about the second row. That's why I'm not going to compute the second row of this multiplication, which is computationally more heavy. So now again, this 0, 1, I'm multiplying by this matrix. The 0 makes these guys disappear. Essentially, we get the second row of this matrix as the first row of the product. And as I have pointed out, we don't care about the second column, the second row of this matrix. So I put it as the stars. We don't know what they are. It doesn't matter. Now, this equality says that 0, 1 is equal to this matrix that we have computed, sort of, times the initial pair. That means the first component, which is 1, is 197 times negative 2 plus 79 times 5. So that's one way of writing this GCD as an integer linear combination of the numbers 179 and 79, 197 and 79. That answers this example. Now we see how we can use Euclid's algorithm in order to find solutions to certain Diophantine equations, linear Diophantine equations. Now let's see basic properties of GCD. The following theorem actually is an important theorem about GCD. It's quite intuitive, but the proof is a bit subtle. So suppose A and B are two non-zero integers, and D is the greatest common divisor of A and B. This means this is the largest common divisor. That's it. Among all the divisors that A and B have, this should be the largest one. So it's quite intuitive to imagine that if I divide A by D and divide B by D, they should not have any other common divisors. So that is the content of this statement, that if GCD of A and B is D, then GCD of A over D and B over D is 1. They cannot have any other common divisors. Okay, so why is that the case? And this is in fact if and only if this is one way of proving it. There are other ways as well, but let's go with this way. So suppose GCD of A and B is D. In particular, D is a common divisor of A and B. And moreover, we proved that GCD of two numbers can be written as an integer linear combination of A and B. So D is also an integer linear combination of A and B. That means there are integers R and S, so that D is R times A plus B times S. Now, because D divides A and D divides B, I can divide both sides by D, and notice that A over D and B over D, both of them are integers. So these are integer numbers, and 1 is going to be an integer linear combination of A over D and B over D. So that implies that A over D and B over D should be coprime. Why is that the case? Because if D prime is a common divisor of these two numbers, if is the greatest common divisor of these two numbers, it's a common divisor. We proved that a common divisor divides every integer linear combination of those two numbers. Because D prime is a common divisor of A over D and B over D, it is a divisor of the integer linear combination R times A over D plus S times B over D. But this integer linear combination is 1. So D prime should divide 1. D prime is also positive because it's GCD. It's a positive integer that divides 1. It is 1. That implies that GCD of A over D and B over D is 1. So if A and B, if GCD of A and B is D, then GCD of A over D and B over D is 1. They are coprime. Now we want to say that this greatest common divisor can be interpreted in terms of divisibility as well. Meaning, if D is the greatest common divisor of A and B, then every other common divisor of A and B divides D. So if D is the greatest common divisor of A and B, is the largest one among all the common divisors, in respect to the partial ordering of divisibility, it is also the largest. So that's a technical way of saying that if D prime is another common divisor of A and B, then D prime should divide D as well. Okay, let's see how the proof goes. We have proved that the GCD can be written as an integer linear combination of A and B. Now, if D prime is a common divisor of A and B, then D prime divides every integer linear combination of A and B. In particular, it divides RA plus SP. So D prime divides D. So this shows that if I consider common divisors of A and B and order them partially with respect to divisibility, when I say partially order them, this means, okay, so if I give you two integers, I cannot always say one of them divides the other one. So 2 doesn't divide 3, 3 doesn't divide 2. But here, the largest one that I pick among the common divisors, every other common divisor should divide. Okay, now, the last property of GCD that we want to mention is the following, that as I multiply a pair by another non-zero integer, the GCD is multiplied by the absolute value of that new integer. So GCD of AC, BC is the same as the absolute value of C times GCD of A and B. So as I've mentioned, all of these results are quite intuitive, but the proofs are often subtle and one has to pay attention to them. So if one proves the unique factorization of integers into primes and interprets GCD and in terms of the powers of the primes that appear, these proofs become much easier. But of course, those arguments, some of those arguments depend on some of the properties of GCD, in particular Euclid's lemma that we are going to prove later using these theorems. So one has to be slightly careful when one is using those results to prove these statements. In any case, so I'm giving you 3 non-zero integers, A, B, and C. Then the claim is greatest common divisor of AC and BC is the absolute value of C times GCD of A and B. So suppose D is the GCD of A and B. Then again, as before, D is a common divisor of A and B, and moreover, D can be written as an integer linear combination of A and B. Okay, but I want to show that these two integers are equal. What I'm going to do, I'm going to show that this side is at most this one and vice versa. I'm going to show two inequalities in order to get this equality. Okay, so the first thing that I notice is that D divides A, D divides B. Therefore, D times absolute value. You see, absolute value of C is either plus C or negative C. So when I multiply D by C, let's say, because D divides A, of course, DC is going to divide AC. Negative DC is going to also divide AC. So in either case, D times absolute value of C divides AC. Similarly, D times absolute value of C divides BC. So this integer is a positive common divisor of AC and BC. Because this is a common divisor of AC and BC, it cannot be more than the greatest common divisor of AC and BC. Therefore, D times absolute value of C is at most GCD of AC and BC. Again, notice we are heading to proving this equality. This is my D. This means I'm trying to show D times absolute value of C is equal to this side. And so far we have discussed that this side is at least this side. We showed that GCD is at least absolute value of C times GCD of A and B. So now let's go back to the result that we have proved about GCD, meaning that because D is GCD of A and B, it can be written as an integer linear combination of A and B. Let's multiply both sides of this by absolute value of C. We get that D times absolute value of C is an integer linear combination of, okay, so it is RA plus SB times absolute value of C, absolute value of C. Remember, absolute value of C is either plus C or negative C, plus C or negative C. So I can factor out the sign of C. It's either plus or minus. And I get that it is R times AC plus S times AC. Ah, this is BC. And this, inside the parentheses, this is an integer linear combination of AC and BC, and this is plus minus. It's again an integer multiple. So altogether, this side is an integer linear combination of AC and BC. Now notice, the GCD of AC and BC is a common divisor of AC and BC, and therefore it divides every integer linear combination of AC and BC. In particular, using this equality, GCD of AC and BC should divide D times absolute value of C. So GCD of AC and BC divides D times absolute value of C. But remember, D times absolute value of C is a positive integer because D is GCD, absolute value is positive. So this is a positive integer. This positive integer is divisible by this positive integer. So therefore, this cannot be more than this one. Now, this cannot be more than this one, and we have the other way around as well. So altogether, we get equality. So these two positive integers are equal, and that's exactly what we wanted to show. So these are equal, and that's exactly what we wanted to show because D is GCD of A and B. So as we multiply a pair of integers by another non-zero integer, the GCD is multiplied by the absolute value of this integer. Now we are ready to prove Euclid's lemma as well, which plays an important role in proving unique factorization of integers into prime numbers. We are not going to prove unique factorization of integers into prime factors, but it's actually rather easy to deduce it using this Euclid's lemma. I encourage you to try it on your own, just in case you have forgotten it. So what is Euclid's lemma? It says that I give you three integers, a, b, and c. Suppose a and b are co-prime, so their greatest common divisor is 1. If a divides a multiple of b, then a should divide that multiple, that's c, because a and b have nothing in common. If a divides this product and a has nothing multiplicatively in common with b, we should be able to disregard b, and all what we need is already inside c. That is what Euclid's lemma says. So if GCD of a and b is 1, a divides bc, then a divides c. This type of result we will be using later when we want to understand order of elements inside a group. Okay, so let's see how we can prove Euclid's lemma. So again, and by assumption, GCD of a and b is 1. We know greatest common divisor of two integers can be written as an integer linear combination of those integers. So 1 is an integer linear combination of a and b. So there are integers r and s, so that 1 equals to r times a plus s times b. Now I'm going to multiply both sides by c. This is a quite beautiful, a bit magical proof. So we are going to multiply both sides by c. So please pay attention to the proof. It's quite non-trivial. So again, the assumption is that a divides b times c, and a and b are co-prime, and I want to deduce that a divides c. And the trick is to write down c as a linear combination of a and bc. From there, we deduce that a divides c. So how do we get to that result is using the fact that when a and b are co-prime, then 1 can be written as an integer linear combination of a and b. We multiply both sides of this by c. We deduce that c is rc times a. You see, I took this c, put it in the middle, because I want to emphasize that this is a multiple of a, plus s times bc. So again, the c that's multiplied by this term, I put it close to b. So the way that I wrote it here should make it clear that c is an integer linear combination of a and bc. In particular, because a divides this and a divides this, remember a is A divides B times C. A divides this and A divides this. We deduce that A divides every integer linear combination of A and BC. Therefore, A divides C. So A divides this, A divides BC. A divides every integer linear combination of A and BC. Therefore, A divides C. And that's exactly what we wanted to show. The reason that Euclid was interested in this lemma was because he wanted to prove a unique factorization of integers into primes. So let's recall what are prime integers and what are prime numbers. Prime numbers are kind of the atoms of integers in terms of multiplication, meaning these are those integers that cannot be factored further. Now we want to say that every integer is made out of these atoms, which is quite non-trivial, right? So, I mean, in a unique way. I cannot make up two different type of atoms and then end up getting the same combination. This is what's hidden in the proof. I mean, what we get out of Euclid's lemma. Okay, so again, let's go slower. An integer p is called prime if, first of all, it is more than 1, and second, it has exactly 2 positive divisors. One of them 1, the other one p. Remember, p is more than 1, so p is not the same as 1. And 1 and p, both of them are definitely divisors of p, no matter if it is prime or not. Now, the claim is that it has no other positive divisors. So there is no other positive numbers. There is no integer between 1 and p, strictly more than 1, strictly less than p, that divides p. That's the definition of prime number. Alternatively, I can say it like this, that if d is positive and d divides p, then d is either 1 or p, and p is more than 1. Now, Euclid's lemma has this consequence for prime numbers, and sometimes this formulation for prime numbers is called Euclid's lemma, but I prefer to have them separately, and I call the first one Euclid's lemma, the second one Euclid's lemma for prime number case, and for prime numbers. Because we are going to need both versions, it's important to have both formulations. So suppose p is prime, and I happened to have 2 integers where their product is divisible by p. Then claim is either p is divisible by a, either a is divisible by p or b is divisible by p. So it's kind of like saying that if combination of 2 materials have an atom p, then p should appear as an atom in one of them. You cannot have 2 materials, none of them having the atom p in them, and then their combination happens to have the atom p. Okay, so that's the claim. I don't make the claim for the materials, but I'm making this claim for primes and thinking about them like atoms. Okay, so p divides ab. Now I want to say that either p divides a or p divides b. Suppose p doesn't divide a. Then I have to show that p divides b. Okay, so suppose p doesn't divide a, but p divides ab, and I want to show that p divides b. But let's see what this implies. Let's look at the GCD of a and p. So the claim is that if I give you a prime number p and prime number p doesn't divide an integer, then they are co-prime. That's the first thing that I'm going to show. The proof is rather easy. That's why I didn't separate it as a separate lemma. I didn't write it as a separate lemma. So p is a prime number. It doesn't divide a. I look at the GCD of p and a. It cannot be p because I just told you that p doesn't divide a. So it cannot be a common divisor of a and p. Now, this is a positive divisor of p. And it's not p. And p is prime. So it's 1, because we just said that a prime number has this property that a prime divisor, a positive prime divisor, a positive divisor of a prime number is either 1 or p. Now this one is positive, this one is not p, and it's a divisor of p, so it should be 1. So if p is prime and doesn't divide an integer, then they are coprime. Okay. Now p and a are coprime. P divides a times b. By Euclid's lemma, it can disregard a, and p divides b, and that's exactly what we wanted to show. Okay, now we are ready to understand a multiplicative structure of integers modulo n, and we'll come back to this in the next video. But I leave this video with this picture of cutting a rectangle to squares till we reach to a square shape chocolate, and that would be the largest tile, square tile that can cover this rectangle, and that would be our GCD. Till the next lecture.